We're live right now. We're live. Hello, everyone. So my name is Kenzie Dodds, and I'm here with Bradley. Bradley, what is your last name? Farias?
Yes.
Is that right? Farias?
Yeah.
Cool. So Bradley's gonna convince me that generators are awesome. So take it away, Bradley.
I'm more just gonna say you're probably using them wrong.
You're probably right.
This is pretty much to everybody who I ever talk to with generators. So don't feel bad in any way or form. They're hard to understand. Um, so the general use case that people find for generators is walking an AST. So that's doing things like code mods or some sort of static code analysis. And so we're going to talk about that in particular and what's special about generators. Um, so here I have this walk combinator class that I use to basically do combinations of AST walks. And you'll notice a few things in my walk generator for this class, the thing that actually walks it. One is I'm not using a for of loop. If you're using a for of loop, really you're just wanting an iterator, not really a generator. So that's going to be a misleading thing. And when I say people want an iterator, people often think of iterators and generators as being the same thing. So they constantly use examples like the Fibonacci sequence, but that's not really what generators are about. That's more what an iterable or iterator is about.
Yeah, and it's like one of the least practical things I can think of, too.
Yes, there's that too. This is also completely impractical and completely slow, but it has some interesting advantages versus functional programming or streams or any of that. So whenever you're using a generator, you need to be considerate of what you're doing. In particular, generators are bidirectional, meaning you can get values out of the generator by yielding an expression, but you can also push values back in the generator by using .next here. So, yeah, that's a bit interesting. So if you're not pushing values back into the generator, that's another reason you should probably be looking at an iterable instead of a generator. Because generators are basically, imagine having two people and they want to have a conversation. There are a few things that can happen here, but we're going to talk about two people having a conversation in the context of them being two generator instances. When one is talking to the other, generally they're passing information. They're talking, saying words. However, they could also say something rude or offensive to the other one, basically like throwing an exception. And the other person may be able to recover from that, back off, or they may leave the conversation entirely, either because they're upset, such as rethrowing the exception, or just because they are no longer interested, which is basically like returning. And generators can encapsulate all of that strange logic of two communicating systems. And so we're going to use that in our AST walker. So in general, what you're going to do is you have something like this while true loop, basically saying, hey, until I've decided to stop from my own logic, just keep doing this pattern. And so we're going to take the opposing generator. In this case, it's from visitor.inputs. And we're going to pass it a command. When we first started up, we just basically have nothing to say to them. They haven't interacted with us, so it's set to undefined in our case. And then if the response from the other person makes us decide that we are done with them, in this case, when we're talking between the two AST walkers, all we're checking for is the other AST walker done traversing an AST. So if the other one is done, then I should consider myself done, is what this line says. And so that's when my generator returns and backs off. So this is the part where nobody really learns what this yield star operator does. So we introduce a third generator from visitor.outputs. And we give it this yield star. Basically, what we're doing is we're saying, hey, whenever somebody talks to this walk generator instance, what we really want to do is we want to hand all the conversation to this other generator, visitor.outputs. And when visitor.outputs is done talking to somebody, because it's basically giving our walk generator a command of some kind, telling us probably, hey, you need to go talk to someone else, or I need confirmation. In terms of UI, it could be saying, hey, I'm walking this AST, but I need the user to interact for some reason. So I'm going to actually run this code I wrote yesterday, and we'll see if it actually works. Need to open up the actual console. Woo. Node, example, or no, this isn't the test. Lint. And it's going to ask me to input some line of source code, and this linter, all it really does is check for you trying to use this, and it complains. So you'll see I've actually used this generator sequence to generate a command telling me something to do, and we'll look at how that's done in a second. Basically, the command is this thing with the less than symbol. So we see it coming out, and then we prompt the user, hey, this is found. And so we haven't actually bailed out on walking the whole AST. We're still mostly done walking the AST. And that's the real advantage here. Unlike a lot of functional or pure immutable based programming where you bail out entirely because some error condition, here we can actually preserve the state, which makes things faster. Unfortunately, most engines until recently haven't been able to optimize generators very much. That's going to change for Node in Node version 9 when Turbofan and Ignition land. But until then, you will be paying some price for using generators. So let's take a look at lint for a second, just so we've seen that there's this kind of interaction going on. So we have our little AST walkers, and whenever our AST walker outputs some path, we're going to do some simple logic. We're going to check, is it a this expression? If it is this expression, we're going to send a message, and we generate the message, and then we do something a little weird here. We go and we yield the message. That's generating the command that we saw earlier. So that's going to be this CMD value when we yield it. Not the CMD value here, but we'll see in a second. If we get back something saying yes or no, then we know what to do. We can break out of the loop, or we can throw because it was an error condition. If we didn't encounter this expression, we're just going to bail and just say, hey, pass the value onward. Any command you receive, pass that on as well. This has a similar-ish thing. It's got this pass-through little thing going on. And it's just a logger of some kind. So you can actually start piping things around and get good info. So what does it look like to consume these walk combinators, which are basically a room full of generators talking to each other? So we made our list of things that need to talk to each other in what order they have priority. We generate a walk for that. And that's basically saying, hey, we're preparing to do a walk, generate this templated room with all the generator instances you want. And then it's pretty simple. Whenever we get a line, and initially we're just going to call next, which basically says continue the walk until you get a command. And next we'll try to walk. If it didn't finish walking, basically if there is a command that's coming in, we want to prompt the user with that command. So yeah. Otherwise,
could you explain that last little bit a little more?
Sure.
Like user interaction for that.
So here, when we call walk.next, that's basically we're waiting on the generator to yield or return. And so if you've used generators programmatically before, this is not too dissimilar to that. The difference here is while we're walking, we're delegating. So let's step back a second. We have this here, and let's walk through what happens. First thing that happens is we're going to be passed in the input, and that's going to this print IO command. And so it's going to go, it's going to say, hey, you're clear to pass through me, which is the yield, and hey, please return any command that yield got. And then it goes to this walk combinator depth first. So it's a depth first traversal that we're doing. The depth first traversal is going to be working on the root here.
And that root is based off of the input that I've typed in to your CLI, right?
Yes.
And so you read that line in. That's the source code. You parse that source code using what?
ESPrima in this case.
Yeah, ESPrima, and then you take that AST and you walk it with your different.
So kind of.
Yes.
So instead of trying to do this walk, which is what you would do functionally or recursively normally, what we're actually doing is we're like sharding it out, basically. So when I say walk combinator.depth first, that's going to see the root, and it's going to pass all the nodes to the next combinator in depth first order. So lint undefined will see the deepest node first, and then the next deepest, and so on until it gets to the very root of the AST.
That's interesting because that's like the opposite of what Babel or ESLint do, right? They start at the top and go down to the leaf nodes.
Yes, and I can explain why that is a problem in a second once we look at the second program, which I don't know if we have time for. But basically, it gets through all this. It gets to the end of the list, and all the inputs by default, unless you specify something else, are going to do this pass through and become outputs. And then it's going to walk back up and fire any of these output generators that we've set up. And so it's going to walk all the way up until we finally get to print IO again. And we see the final output. So what happens if we yield in the middle of this? Particularly if we yield during lint undefined, the depth first is currently in a yield star to our lint undefined. And so that's going to mean any yield in this is going to cause the entire combinator to yield and bail out. It's not going to finish the walk, but it'll keep all the state we ever had. And so that is the return value, what we yield here.
And so in that case, here I'm going to focus on your screen. So in that case, the yield or return value .done is going to be false. Could you go back to that code that?
Yeah. Go down here.
Yeah. So when I yield, the return .done is going to be false, and so then we'll go look at the value if it's a string, and in this case it's a message, right? It's that message string that you created. You're yielding that message. So it's going to be a string, and we'll prompt the user with that error message, whatever, will prompt them to do something else. So in that situation, like I don't want to traverse the AST anymore because they're going to provide me a new AST, right? Is that?
No, this is purely saying if you approve or disapprove of this instance in this example. So we have made it, let's say, 50% through the AST, and we don't need to reparse unless they reject us for some reason. And so this prompt is going to pass back into here. And so
okay, that makes sense.
They type something in. We get the command back from them saying if we've exempted this warning or not. And that's when we can continue our walk without starting from the beginning, or we can bail out because something truly was wrong.
Yeah, that makes sense.
So this behavior is interesting because even if we throw an error here, it'll throw at this point, and you can actually go and catch it in other combinators. So you can halfway bail out your AST walk if some phase knows how to recover from the error.
So what happens in this scenario? So like if I, as a user, I type no, that's not okay. This throws, or that the visitor throws, and then because this isn't handling the error, my walk will throw. So who's catching that?
That's going to bubble all the way out and bail when Node sees the error.
I see.
You could handle it yourself, though. But eventually, it just bails out because we don't have any try-catch around this little thing. So this is very, very complicated thing going on here, but do you know what constant folding is? It's a compression technique used by Google Closure Compiler, but not used by Uglify, which basically states if you have some values, let's say 1 plus 2, that's going to become 3. And Uglify does this to a lesser extent than Closure Compiler, but Closure Compiler takes it further. Maybe C0 will go to A. So it actually does some calculation involved. However, Closure Compiler and a lot of these other techniques for walking the AST don't have something called a reentrant walker. Reentrant is kind of a term that I picked up from AI. It basically means you can do part of the work, decide you need to throw something away, say you need to replace some node 1 plus 2 to 3, and then continue all your steps again. So if I had 1 plus 2, that's going to become 3. But let's say I need to do it before I OR with something else. If I don't have a reentrant combinator, it's very hard to figure out after this becomes 3 that I can once again reevaluate this.
Oh, that's why you were asking me about if I had any code mods that change state, right?
Yes.
Yeah, because this would change. Like this would be a visitor that actually changes the state as it's traversing, and it would be really difficult to keep track of that state in a way that you could continue making modifications. Actually, this is really applicable for the Slice.js tool that I've been working on, because I'm making modifications all the time, and I pretty much wind up just rerunning my plugin on the same code a couple times. ESLint actually does this. If you have a fixer on ESLint, they wind up running all of the plugins up to 10 times if there are changes.
So let's look at one of mine for a second and compare to what you've seen before. What's a good one? Logical should be good. Logical statements are pretty simple. Basically, we have some code. It checks, is the current path that I am running my folder on a logical expression? That's a or statement, an or expression or an and expression with the double pipes or the double ampersands. We do a few things here. We check if it's constant on the left side, and then we transform it into, should it return the left or right side of our operator. You'll notice something here. I have this replace, and I return it. So in this walk combinator, whenever I return a value from a generator and I don't yield, it's going to bubble all the way up, and then it'll retry just on whatever the left side is of this. So it's basically saying, hey, I've modified the subtree of path. You need to go rerun all the steps on that subtree. Does that make sense?
This happens just because of this magical replace function that you have, and it's...
No. Replace actually, it should be up here. Just returns like this little structure, deletes what used to be there, and like wraps it with the current path that it is replacing. It's not magic.
I see, but because the user of this replace function is a generator, when it returns that new node path, the consumer of that generator is going to rewalk across.
Well, the consumer gets the command back, which it sees as a node path, and it knows if I get something back, I need to retraverse everything.
I see.
So it's all back to this command thing and passing things around. So we're basically having all these different phases, which are in here. All this like fold empty, fold expression statement. These are all generators that are being applied to all the nodes. And so if you imagine a room, it's basically having a specialist for each phase of this. And fold empty, let's say these are prioritized in order that they appear. Fold empty will see a path and say, oh, well, this could be better. And then it passes it back to the drawing board. And then the drawing board comes over, passes it back to fold empty, and it's like, well, I can't optimize something I've already optimized. So it passes it to fold expression statement. Say fold expression statement can't optimize it, it'll pass it to fold while. Fold while will return a replacement if it can optimize the path. And so it's basically, oh, back to the drawing board, which is not the beginning of the AST, actually. It's just the beginning of the walk at the current path. So instead of walking all the way up to the root node, we could only be walking up 4 or 5 nodes that need to be redone.
Yeah, that'd be much faster, especially in a bigger program. That makes a lot of sense.
So yeah, this is what generators are supposed to be used for.
Yeah, I'm trying to envision trying to like implement something like this in Babel and not even knowing the code of Babel or ESLint, and it just seems like it would be really, really difficult to maintain that state yourself.
It is super difficult. So there are bugs in Uglify, Clojure compiler, and Babel. But like I said, generators have a cost. Most VMs don't optimize them heavily. But even at that cost, even though generator functions have optimization disabled entirely in the version of Node I'm running, it's still competitive or faster to use this system. Just because you're doing so much.
If we care about the future, then may as well like go with the path that is going to be optimized, right?
Hopefully, yeah.
Yeah.
But that's it. That's all I got.
Well, that's really cool. That was really interesting. I love ASTs, and generators are something that I am not used to. So I appreciate you showing me that.
Cool.
That was interesting.
All right. Well, I gotta run, so I will talk to you later.
Cool. Thanks so much, Bradley.
All right. Bye.
Bye.